Hi, I'm Ben. Welcome to Rust Curious, where I explain Rust carefully. Today we're learning about generics. You know, those things in angle brackets like a type parameter t. Generics are absolutely pervasive in Rust. The standard library is full of them. There are two goals behind using generics. First, with generics we can make code that's reusable. So you can have a collection type like vec that can hold items of any type. The implementation of vec gets reused no matter what type of items you're storing inside the vec. And you can write your own generic types and generic functions that do the same thing. Second, generics help with finding problems at compile time. When you have a vec that contains bytes, that's a distinct type from a vec that contains strings. The compiler tracks what the type is and checks that it's used consistently. So if you try to put two different types of items into a single vec, you'll get a compile error. Or if you take an item out of a vec and treat it as something different from what went in, you'll get a compile error. And I much prefer finding stuff like that at compile time rather than having to debug at runtime. If you've been following along in this channel, you've already seen some examples of generic types in use. Vec, option, and result all have generic type parameters. There are two other kinds of generic parameters allowed in Rust: constant parameters and lifetime parameters. We're going to save lifetimes for another video. That's a whole can of worms on its own. So in this video we'll cover type parameters and constant parameters, and that'll provide a solid foundation for lifetimes when we get up to that. As always, we'll finish with a practice exercise for you to try out, and this one is a little more challenging than in previous videos. We're going to implement our own little collection type called a slab. It pulls together structs, enums, and arrays with generics, and I hope you'll find it to be a satisfying way to integrate everything you've been learning. As well as how to use generics, I want to give you an understanding of what the compiler generates when you use generics. That process is called monomorphization. It can lead to increased binary sizes, so I'll show you some ways to minimize that. But also, understanding monomorphization helps you develop a thorough understanding of generics. Curious? We'll start with standalone generic functions, then we'll cover generic types and methods on generic types. And finally we'll get into that practice exercise. It's a good one. Let's start with something simple. Here's a function foo i32 that takes an integer and just returns that same integer. Yes, this is useless, but bear with me. Here's another function, foo char, that does the same thing but with a char. Now imagine we want to do this useless thing with any type. Instead of writing another function for each type, we can instead have a single generic function. This function foo has a single type parameter t in angle brackets. The angle brackets go right between the function name and the parens for the normal parameters. And this function declaration says that for any type t, you can call foo with a value x of type t, and it will return a value of the same type t. So if I call foo with an integer, then I get back an integer, so a is 10. If I call foo with a bool, then I get back a bool, so b is true. It looks like I'm calling the same function both times, but I think it's more helpful to think of foo as a family of functions. Each member of the family handles a different type for t. So foo i32 handles integers and foo bool handles bools. And I can make the type t explicit on each call, but this is not quite the right syntax. It'd be nice and consistent if it looked like this, but unfortunately this would make the grammar ambiguous. When we're declaring the function, the angle brackets are fine, but when we're calling the function, we are in an expression context, so these could be interpreted as the less than and greater than operators. To make this unambiguous, we have to use this syntax. The double colon makes it clear we are writing angle brackets here. We are explicitly specifying the type t. Yes, this is a bit ugly. It's kind of a wart in the language. It's become known as turbofish syntax, and if you go to turbo.fish, you can watch live footage of the Rust compiler resolving generic types. Usually you don't need turbofish syntax. You don't have to make the type explicit because it can be inferred from the value you're passing in. That's what happened when we called foo with the values 10 or true. But sometimes that's not possible. For example, the standard library provides the sizeOf function, which returns the number of bytes needed to store a given type t. SizeOf doesn't take any parameters, so there's nothing to infer the type from. And if you call it without specifying the type, that's an error. The only way to call it is with an explicit type using the turbofish syntax. We could use sizeOf to make the foo function slightly more interesting by printing out the size of t. Why not? Inside foo, I can use t anywhere that accepts the name of a type. So n is the size of t, and we can print it out. When you declare a generic parameter name in angle brackets on a function, that name t, in this case, stays in scope until the end of the function. So I can use t in the parameter types, in the return type, and in the function body. As I said earlier, I want you to think of this generic function foo as really a family of functions. Each time you use it with a specific type for t, you're choosing a particular member of the family. And the compiler treats it that way. So if you look at the code that gets generated, when you call foo with an i32, the compiler spits out a version of foo with i32 everywhere that said t. And when you call foo with a bool, it spits out another copy, but this time with bool substituted for t. If you called foo with a string, you'd get another copy for that type. This process is called a monomorphization. Foo is a polymorphic function. It comes in many shapes. Monomorphization happens each time you need a version of the function for a specific concrete type. Now, you might be worried that if you call foo with a string in 5 different places, you'll get 5 copies of foo for strings. Don't worry, the compiler cleans up redundant copies, so you'll only end up with 1 copy of the function for each distinct type that gets used. That said, monomorphization can lead to code bloat. The basic advice for reducing that bloat is to keep code out of generic functions if it doesn't need to be there. Let's say foo has a big chunk of code with some nested loops or whatever. That chunk of code will get duplicated each time foo is monomorphized with a different type for t. But most of this code doesn't actually handle any variables of type t, so it's a candidate to be pushed out into a separate function. Now we have an ordinary function called doStuff. It's not generic, and we're calling it from the generic function, so that logic is no longer duplicated each time foo is monomorphized. Now, at this point you might be thinking, Ben, your examples today, they kinda suck. Usually you come up with something relatable, but a generic function foo that just calls doStuff and then returns whatever it was called? Come on. Okay, fair, but in my defense, this is a little tricky because if you have a value that could be of any type, then what can you really do with it? In fact, that's a good question. What are all the things that you can do with a value of type t that could be any type? Can you copy it? No, some types can't be copied, so a value that might be of a non-copyable type can't be copied. Can you clone it? No, same answer, only some types can be cloned. Can you add 2 of them together? No, addition is only defined on certain types. If you have a value that could be of any type, you can move it from place to place, you can destroy it by letting it go out of scope, and you can use it with any other generic functions that accept any type without constraints. So for example, you can store it in a vec or some other collection type. All those other operations, copying, cloning, addition, those are all defined by traits. You can use traits to write generic code that can work with any type as long as it has particular capabilities. The next video will be all about traits, and I'll give you a little taste of that in a minute, but first I want to show you another kind of generic parameter. So far we've just been looking at generic type parameters. Rust also supports generic constant parameters. This function, blat, has a generic parameter called n, which must be a usize. Const means this value must be a constant at compile time, and because it's known at compile time, it can be used in types. So this function returns a fixed length array of n integers. Just like with type parameters, I want you to think of this as a family of functions that all have the same name, but with different values for n. In each place this function is called with a particular value for n, it will be monomorphized for that value, producing a function that returns an array of that specific length. So if I use turbofish syntax to call the function with n set to 4, I get back an array with 4 elements. That value for n must be a constant at compile time. If I try to call this in a loop with a variable for n, this won't compile. It's not a constant. And that makes sense because if it did compile, what type would the array be? The loop body is a single piece of code. It can't have a different type each time round the loop. A const generic parameter can have any type, but the one you'll see most often is usize. That's because const generics are so useful with fixed length arrays, and array length is always a usize. This stuff is particularly handy in embedded firmware when you want to avoid dynamic allocation like what you'd get with vec. A single generic function can combine type parameters and const parameters. In the video on arrays, we used a function called repeat from the standard library to create a fixed length array by cloning a string for each element. Here is how that function is declared. It has a type parameter t, the element type, and a const parameter n, the length of the array. At runtime, it takes a single value of type t and it clones it repeatedly to fill the array. And the only reason it can do that is because it has an additional restriction written in this where clause. It doesn't work with every possible type t, it only accepts types that have the clone trait. Again, next video, lots more to say about traits. In this example, I made the type of the array explicit. That way we don't need any turbofish syntax to call the repeat function because it infers the generic parameters from the context. If I remove the type annotation, this doesn't compile. It can still infer t from the fact we're passing in a string, but it has no way to know how long the array should be. I can use turbofish syntax to specify t and n, and this works fine. But also, I didn't really need to specify that t is a string here because we already get that from the value that's being passed in. So if I'm lazy, I can just put an underscore there, which means, compiler, you figure it out. Do the type inference thing, and this compiles. So far we've seen generic functions with type parameters and const parameters. I started with generic functions because they're simpler and it makes it easier to understand monomorphization when you're talking about one function at a time. But of course, most uses of generics are focused on generic types, like collection types, so let's get into that. This is the part where we look at generic collection types like vec, and we set you up for the exercise where you make your own little collection type. But again, let's start simple. You've already seen the generic enum option. Just like a function, the angle brackets come right after the name. So option has a type parameter t, and it may or may not contain a value of type t. The variant none is empty, and the variant sum contains a value of type t. You can even think of this as a collection type that can hold a maximum of one item. The generic enum result is similar, but it's for operations that can fail. So if things go well, then you get the variant OK with a value of type t. If things go badly, then you get the variant with an error value of type e. So this is a good example of a generic type with two type parameters. Just like option, result is so important that it's already in your namespace, and the OK and variants are also already in your namespace. So you can construct these variants very easily, and we use them all the time. If you go to rustcurious.com, you'll find this map of the type system called the elements of Rust. Option and result are built into the language, so here they are. And you can click through to the official documentation to see all the methods available on those types. There are many. Okay, how about a generic struct? If I want to loop over integers, I can say for I in 0.10. If I want to loop over chars, I can say for c in a.z. In both cases, this ... syntax is an expression that produces a range, and that range is a value, it has a type. A range is a struct that stores the start and end values, but these two examples have different types for those values. Here is how the struct range is declared. It's a generic type, so it has angle brackets right after the name, and this time the type parameter isn't called t, it's called idx, short for index. But whatever, it's just a name. So this says for any index type you can have a range with a start index and an end index. The only constraint here is that the start and end both have to be of the same type. To construct a range, I can just use the ... syntax with the start and end values. If I want to be explicit about the type, range comes from the studops namespace, and I can write the type name with the index type in angle brackets. And notice we don't use turbofish syntax here. We don't need to write any colons before the angle brackets. That's only needed in expression context. In this case, we're writing a type ascription. We're not calling a function. To construct the range, I don't have to use ... syntax. It's just a struct and the fields are public, so I can instead construct a value with curly braces and a value for each of the fields. And notice here that I don't write any angle brackets, I don't specify any generic parameters. I just give the name of the type and the values for the fields. If I don't want to write the type ascription, but I do want to make sure the index type is i32, I can make either or both of the values an i32 in the expression. You might remember from video number 2 how a scalar literal can have an explicit type just like this. So that's the built-in range type. Let's make our own generic struct. This struct is called stack. It has a generic type parameter t, and it holds a single field called inner with a vec of t. Now, in many cases, you could just directly use a vec as a stack, but maybe you want to restrict the API that's available to clients. Maybe you want to give it some special integration with another API in your project. So we're making a wrapper around vec with an API that we control. Now, how do we write methods on our generic stack type? Well, you might think you could write an impl block like this to implement methods on stack t, but this does not compile. We get an error that points at the t in angle brackets and it says cannot find t in this scope. So when we declared the struct stack with a t in angle brackets, that name t is only in scope until the closing curly brace at the end of the struct definition. And now when we come to writing an impl block, this is not a place where we can declare a generic parameter. In this situation, we are saying what type we're implementing methods on. If I just leave out the angle brackets, I get a different error, missing generics for struct stack, expected one generic argument. So I have to specify a type. If I say I'm implementing methods on a stack of i32s, then that's fine, the compiler is happy. But what I want is to write a single impl block that can work with any type. To do that, I have to write a generic impl block. Impl t stack t. The first set of angle brackets is declaring a generic type parameter t. This is the part that says for any type t. The second set of angle brackets is where I'm using that type to implement methods on stack t. So now I can write a new function that constructs an empty stack. It just calls vec new to create an empty vec. And I can write a push method that adds an item to the stack. It takes self by mutable reference and an item of type t, which we just pass to the push method on the vec. And we can add a pop method that takes the item off the top of the stack if there is one. So it returns an option t, and again we just call the pop method on the vec and return that. The generic parameter t that I declared at the top of the impl block stays in scope for the whole impl block, so I can use it in these methods. All the functions in this impl block are generic functions because they're all inside a generic impl block. That means each of these functions gets monomorphized just like a standalone generic function does. When one of these functions gets used with a particular type, the compiler spits out a copy of the function with t set to that type. To use this stack, I can just call stack new and then start calling methods on it. In this example, I'm calling push with an i32, so type inference can see this is a stack of i32s. I could instead make the type of the stack variable explicit, stack i32. Or if I wanted to do it in the expression that creates the stack, I'd have to use turbofish syntax to write angle brackets in the expression. You don't see this too often, but occasionally it's useful if you need to give the fully qualified name of a function. Anytime you see a double colon followed by angle brackets, if it's confusing, just mentally remove the double colon to the left of the angle brackets. Then it's obvious, oh, it's just a stack of i32 and we're calling the new function in that namespace. Anyway, as I say, it's unusual to need any of that. Mostly we just let type inference figure it out. Okay, so we made a generic struct and implemented some methods on it. You can do exactly the same thing to make your own generic enum types. The generic impl block works the same way with enums. In the practice exercise, you'll be working with a generic struct and a generic enum. In preparation for that, one more thing I want to show you. Let's say we have a very simple generic struct foo that contains an inner value of type t. And I want to write a method called update that takes a new value of type t that it's going to store in inner, and it's going to return the old value of inner. So, how should I write this method? The challenge is that I want to install the new value and remove the old value in a single operation. I could try something like this. I put the old value of inner in a temporary variable, then I store the new value in inner, and then I return the old value from the temporary variable. Will this compile? No. Error cannot move out of self.inner, which is behind a mutable reference. Self is a mutable reference to the foo, so inside this method we only have borrowed access. We don't have ownership of the foo. We can't move the value out of inner, even temporarily. But we do have exclusive access, and we have a new value we want to put there. This is a completely reasonable thing to want to do, and you might even find yourself wanting to do something like this in the practice exercise. So the standard library gives us two ways to do it. The first is with this generic function called replace. It takes a mutable reference to a location we're calling the destination, and it takes a new value, the source value. It stores the source value in the destination and returns the old value that was previously in the destination. So with this in hand, we can easily write our update method. Replace comes from std_mem in the standard library. We take a mutable reference to self.inner, pass in the new value, it returns the old value, and we return that. Perfect. Another way to do the same thing is with the swap function, also from the standard library. This one just takes mutable references to two locations and it swaps their contents. So this time I'm calling swap with a mutable reference to self.inner and a mutable reference to the new value. And notice for that to work, I put the mute keyword in front of value to make it a mutable variable. So the swap leaves the old value in that variable and I can return it. For this particular use case, the replace function is slightly more convenient, but they both work fine. Keep replace in mind when you come to do the practice exercise, which we're going to walk through right now. In this exercise, we're going to build a collection type called a slab. You'll find the code at rustcurious.com/8. Just click on the button to open it in the playground. And like I said earlier, this exercise is a little more challenging. It pulls together structs, enums, and arrays with generics, so this is a good opportunity to consolidate what you've been learning. The idea of a slab is that it has pre-allocated space that can hold up to some number of items. We're using a fixed length array, and each entry in the array can either be vacant or occupied. The slab maintains a list of the vacant entries, so when you insert an item, the slab chooses where to put it, and it gives you back the index of the new item in the slab. Then you can access the item by its index. The type definitions are provided, and your job is to fill out the method bodies so the unit test passes. Here is the definition of the slab type. It's a struct with two generic parameters, a type t for the items it will store, and a constant n for the capacity, the number of entries in the array. It has two fields, buff and head. Buff is the array, and each element of the array is another type called entry. We'll get to that in a moment. Head is the start of the list of vacant entries, and I'll explain what that means. The entry type is a generic enum, and it's either occupied or vacant. If it's occupied, then it holds an item of type t. If it's vacant, and this is the clever part, it holds the index of the next vacant entry in the list. So the list of vacant entries is like a linked list, but it uses usize indexes instead of pointers. Let's walk through an example so you can see how this is supposed to work. First, we have to initialize this thing. We're going to set head to 0, meaning index 0 in the array is the first vacant entry. We initialize that entry to the vacant variant, pointing to index 1 as the next vacant entry on the list. Entry 1 will be vacant, pointing to index 2 as the next vacant entry. Entry 2 will point to entry 3, and so on. The last entry in the list will point to index n. In this example, n is 4, which is just past the end of the array. We're going to use n as a special value that means this is the end of the list. There are no more vacant entries. So right now, starting from head, we have a linked list that includes all the entries, ending with index n that indicates the end of the list. The point of this list is that we never have to scan the array looking for a vacant entry. To insert an item, we can always just take the index in head. If head is n, then we know there are no vacant entries, so the slab is already full. In your solution, if you find yourself writing a loop, something has gone terribly wrong. This is all designed so you never need to loop, we never need to scan the array. Insertion and removal should both be O of 1, constant time. Okay, let's insert an item. Head is 0, so that's where we put it. We're going to take entry 0 off the head of the vacant list. Right now, entry 0 says the next vacant entry is at index 1, so we update head to point to that. Then we change the entry from vacant to occupied, so now it contains an item of type t. The caller of the insert method gets back index 0, so they can access this item. Let's insert another item. Again, we're putting it in the location pointed to by head, and we're taking that entry off the vacant list. It currently says index 2 is next in the list, so that's what we update head to. And we insert the item. I'm going to fill the slab, so again we choose the entry pointed to by head, update head to the index it points to, and insert the item. Choose the entry pointed to by head, update head, insert the item. And at this point, head is n, which means the vacant list is empty. So if insert is called again, we check head, we see that it's n, so the slab is already full, and we refuse to insert anything. The slab also provides a remove method that takes an index. The client can remove items in any order they like. So let's say the client wants to remove the item at index 1. We're going to make this entry vacant and push it onto the head of the vacant list. Head is n, so we replace the occupied entry with vacant, pointing at index n. And notice I used the word replace there. That might be a hint. So the new vacant entry is now pointing at what was previously the head of the list, which happens to be empty. And now we update head, so now this is the start of the list. Now the client wants to remove the item at index 0. So again, we replace that entry with a vacant that points at the current head, and we update the head. One more time to remove from index 2, replace it with a vacant pointing at the current head, and update the head. So now you can see that the linked list of vacant entries can end up in any old order depending on what the client does. If the client inserts an item now, just like before, we're going to take an entry off the head of the vacant list and put the item there. This entry says the next vacant index is 0, so we update head to point to that and then insert the item. Okay, that was a lot to walk through, but I wanted to make sure there's no misunderstanding about the expected behavior here. The unit test expects the slab to be initialized just like I described, with the vacant entries linked in order. And the insert and remove operations should always update the head of the list, just like I showed you. Coming back to the slab type definition, there's actually a big comment here that I didn't show earlier about the meaning of the head field, and it lists two invariants. If head is less than n, then the entry at index head must be vacant. It is the head of the vacant list after all, so whatever it points to better be vacant. If head is equal to n, then all entries are occupied. In other words, if the vacant list is empty, then the slab is full. The nice thing about invariants is that if you run into a condition where an invariant is false, then it's really easy to handle. You just panic. That might come in handy when you're implementing some of the methods. The method declarations are provided for you inside an impl block that looks like this. And again, we see one set of angle brackets on the impl keyword to declare our generic parameters, so for any type t and any usize n, and another set of angle brackets where we use those parameters to fully specify the type we are implementing methods on. When we declare n, we have to say it's a const usize, but when we use n, we just say n. Okay, we'll walk through the method signatures and then I'm done. It's over to you. There are 5 functions for you to implement. New just returns an empty slab. Remember, self with a capital S is just an alias for the type we're implementing methods on. And you might find it very helpful to use array from fun, which I showed you in video number 7, all about arrays. The insert method takes an item of type t and stores it in the slab. That will fail if the slab is already full. And my question is, what should happen to the item if it can't be stored in the slab? Do I just lose it? That would be sad. So instead, this method returns a result. If the insertion succeeds, we get back a usize with the index where it was stored. If it fails, because the slab is full, then we get back the item. Hooray! So in this case, we're using the slab's item type t as the error type in the result. Next, the remove method. It takes an index for the item you want to take out. It returns an option in case you call it with the index of an entry that's vacant, in which case you get back none. If it was occupied, then you get back some with the item of type t. And because you're pulling a value out of the array, this is where the memReplace function might come in handy. Okay, that's all the hard stuff done. The last two are easy. Get and getMute both take an index and return an option with a reference to the item at that index, if there is one. Get gives you a shared reference, getMute gives you a mutable reference. And again, if the entry is vacant, then you get back none. That's it, that's all the methods. I won't try to read through the unit test, but it's pretty thorough and it's made to be readable. So if you get a panic in the test, look at the line number, look at the line it blew up on, and it should be pretty obvious what state the test is expecting the slab to be in. So you can take it from there. I do hope you enjoy this exercise. When you get the slab working, I hope it highlights that you've put quite a few different pieces together to solve this puzzle. We've covered quite a lot of ground already. Coming up next, traits. So many traits, the standard library is full of them. Traits give us a really powerful way to represent abstractions, so I hope you're excited for that one. Stay curious, and I'll see you soon.